Okay, so this says ethanol, which is an alcohol. It's a colorless, flammable liquid. We have two 1 gallon containers. One is labeled sample A, one is labeled sample B. Each is filled with a colorless liquid. We're assuming one is ethanol and one is water. Could we tell the difference just by looking at them? No, we cannot. They look exactly the same. So we have to do some other assessment to determine if one is water and one is ethanol. So what could we do? We could light them on fire, but that would be pretty dangerous. But that's the goal. Go ahead. Or smell. So I didn't even think about that, but someone in my earlier lecture said that. You could smell and see if you can smell which one is ethanol. If we don't know if it's ethanol and it's some unknown substance, you don't want to smell it because we don't know if it could be harmful. But that is one way to tell. So ethanol should have a scent, water really doesn't. But the other one could be testing its flammability. So lighting 1 gallon of ethanol on fire is pretty dangerous. But if you could take a sample of it and see if that is flammable, we'd be able to tell which one's ethanol and which one's water, because we know water would extinguish a fire and is not flammable. So I'll just right here use its flammability property. And then you could add some extra detail. Ethanol is flammable, water is not, etc. Before we move on, I actually wanted to go back to this slide from a few slides ago. There's one thing I didn't touch on when we were looking at these 4 different pictures of element, compound, heterogeneous mixture, homogeneous mixture. And one thing that I wanted to touch on here is that the element that's represented here almost looks like a compound. We have 2 atoms that are bonded together here, showing the element. But it's listed under element, it's not listed under compound. And that's because for any element, or for any 2 atoms that are bonded together, if it's the same element, like hydrogen gas is H2, or oxygen gas is O2, since that's the same element, 2 atoms of the same element bonded together, we categorize that as an element. A compound has at least 2 different elements bonded. So a bunch of examples here. We have, these are all elements. Hydrogen gas, oxygen, dinitrogen, difluorine, diiodine. What are others? Chlorine, bromine. Even ozone. Ozone is O3. Still all the same element bonded together, so that falls under the element category. There's an Achieve homework question about this, so I just want to make sure you all have that information. That those are considered elements even though it's 2 atoms bonded together. It's because they're the same atom. Any questions about that? Okay, so we started talking about properties of atoms, properties of compounds, which will continue here, and then properties of mixtures. So we said there are physical properties and chemical properties. There's intensive and extensive. Physical is like melting point, color, solubility. There are a bunch of different examples in your notes. Chemical properties are properties like flammability or reactivity with other substances. When we have a compound, so different elements bonded together, properties of that compound are different from the properties of the elements that compose them. When we were first learning about compounds versus elements or compounds versus atoms, we talked about this a little bit, where water, H2O, is composed of hydrogen and oxygen. Here are some properties. I did notice in my earlier class that the second half after the colon is switched. So oxygen at room temperature is O2 gas, which is down there. It has a boiling point of negative 183 degrees Celsius. Hydrogen at room temperature is a gas with a boiling point of negative 253 degrees Celsius. So two gases with really low boiling points, they're gas at room temperature. But water, where we've combined hydrogen and oxygen, is now a liquid at room temperature with a boiling point of 100 degrees Celsius. So its properties are different from the elements that compose it. But when we have a mixture where the components are not chemically bonded to each other, the properties of mixtures are similar to the components that make up the mixture. So a solution of liquid water with sugar is a liquid solution with sugar molecules still dissolved in it. The properties of this, like melting point and boiling point, are different than the properties of water and sugar. But when there's a lot of water and a little bit of sugar, the properties of the solution are more similar to the water. And if there's a lot of sugar where most of this is solid, then the properties of that mixture will be more similar to the sugar. So the properties depend on the amount of each component in the mixture. But again, they're similar to the components that make up that mixture. Okay, I have two videos I wanted to show you. These are both in your book, so this shows you what is available to you if you look at the book. Oops. Hopefully the audio works. Sometimes I have trouble with that here, but I'll explain what's going on if needed. Okay, so a mixture of iron and sulfur, we still have magnetic iron and not magnetic sulfur. Now in the second video, the mixture of iron and sulfur go through a chemical change and a new substance is produced at the end. And then we look at the properties of that compound. So here we have elemental iron, which we know is magnetic, elemental sulfur, which is not, and then they heat it and produce iron sulfide. So a new compound. So we have a new compound that has different properties from the iron that it was formed from. So when we saw the burning or the heating of the iron and sulfur, that was going through a transformation. So we're looking at transformations of matter next. That was a chemical transformation. First, we're going to talk about physical transformations. And this occurs, or when a physical transformation occurs, the substance's physical property changes. So that could be going from a solid to liquid, liquid to gas, dissolving. But the substance's chemical nature doesn't change. So an example I've used before is, or here is the freezing of water. So if we have liquid water, it's still H2O molecules. If we freeze it, it's still H2O molecules that are now just frozen. So the chemical makeup hasn't changed, but the molecule spacing and alignment changes, and that's why we have a liquid versus solid. Another example is that dissolving sugar in coffee. Sugar is a solid. Once it's dissolved in coffee, it's mixed with the liquid water, mixed with caffeine, things like that. When we have a chemical transformation, these are the cool transformations. This is where we can make a completely different molecule, a different product. A chemical transformation produces new substances. So that new substance that's produced, we call that a product of a chemical reaction. And that substance is chemically different from the starting materials, which we call reactants or reagents. The chemical nature of the substance changes. We saw that in the video with iron and sulfur. And then a chemical transformation involves the breaking and or the forming of chemical bonds. When a bond is broken, energy is required for that bond to break. When a new bond is formed, energy is released when the bond is formed. An example here is burning magnesium metal in the air. So magnesium metal, here's a picture of that here, can react with oxygen with heat, and it would form magnesium oxide, which is a new substance. So we go from a shiny, silvery solid to this white powder once it reacts with oxygen. Now the magnesium oxide has different properties from the magnesium metal, different properties from the oxygen. Yes?
So that would release energy upon form?
So this, well, we also have a bond breaking, which is the bond between the two oxygens. So heat is required for this reaction to occur, but if we had a reaction where the energy released when bonds formed was greater than the energy required for bonds to break, then that reaction would release heat. Okay. Any other questions? Okay. So we've talked a little bit about energy. Energy is the capacity for something to do work. One of the laws of energy is that energy cannot be created or destroyed, but it can be converted from one form to another. So an example of an energy change is your cell phone battery recharging. Electrical energy from the outlet is being converted into chemical energy that is stored in your battery. So batteries store chemical energy. Other examples are fireworks exploding, specifically in the night sky for some reason. I felt putting that in there. Penicillin destroying a bacterial infection is an energy transfer or an energy change. A batch of cookies baking in the oven, heat from the oven is causing chemical changes in energy in the cookies. Burning a log on the campfire is a chemical change or an energy change. And there are many different forms of energy. So heat energy we're really familiar with, temperature. Chemical energy is how batteries store energy is through chemicals. Mechanical energy could be kinetic, the energy of motion, or potential energy of position. We have electrical energy, which powers a lot of what we use. Sound energy, and then electromagnetic radiation. So visible light is its own type of energy, radio waves, microwaves, infrared, things like that. So a bunch of different forms of energy. And here's an example of converting energy for using the flashlight app on your phone. There's conversions of energy that are required for that flashlight to be powered. There's energy stored in your phone battery. Batteries store chemical energy. That's converted to electrical energy in your actual device. for you to be able to use it. And then when you turn the flashlight on, that energy is converted to then visible light energy, so we can actually see the light. If you were paying attention, I already answered this question, but think about this. What energy conversion is exhibited when you're recharging your cell phone battery by plugging it into a wall outlet? What type of energy do we start with? The electrical. So the wall outlet provides electrical energy, and that's converted to chemical energy in the battery. So we have electrical to chemical. Yes. So yes, so when we are recharging cell phone batteries by plugging the phone into a wall outlet, the wall outlet supplies electrical energy, and then that is converted into chemical energy, which is what batteries store. They store chemical energy. So we use energy from the electrical outlet to recharge the chemical energy in a battery. Other questions before we go to the next section? Okay. So our next section's a little short. Just introducing the scientific method, which is a general process of how science advances. In reality, doing science is really messy. This shows like a really nice flow chart going from an observation to a theory, but there are a lot of steps and a lot of backtracking and moving forward that really occurs in science. But this kind of deduces everything down into a nice flow chart. So our goal here is to describe the scientific method and then to distinguish between hypotheses, theories, and laws. So question here, how does chemical science advance? How does the field of chemistry advance? And this applies outside of chemistry as well. But we really have goal-driven experimentation. So we perform experiments to reveal chemical properties of matter that might reveal something new. The resulting data from experiments are organized into general principles and theories, maybe by recognizing a pattern in the results, conclusions that can be drawn from the results. And then these principles and theories can lead chemists to make predictions. And these predictions drive further experimentation. And then we repeat the process. So on this next slide, we have the scientific method flow chart, where we can start from observing something, we observe a pattern or we observe some sort of data. Then from the observations, a scientist can create a hypothesis that they think would explain their observation. But to actually see if the hypothesis is correct, you need additional experimentation. So the additional experimentation can either support the hypothesis, then even more experimental evidence is needed, and from other scientists that can generate a scientific theory, as long as there isn't contradicting results. If the results are inconsistent with the hypothesis, then the hypothesis needs to be revised. So again, a really condensed flow chart of what's required. The main thing to think about here is that we start with an observation. We start with observing something that looks interesting or doesn't seem to follow what we already know or is something new. And then we need data to support any sort of conclusion that we're trying to draw from the observation for it to actually be accurate. As long as there's enough evidence that supports the hypothesis, then it becomes a theory. So a little bit more about hypotheses. Oops. A hypothesis is a tentative general principle for it to become a theory, which is a widely accepted principle. It has to be confirmed in two ways. One, additional results must be consistent with the hypothesis. So anything contradictory means the hypothesis is incorrect. And then the hypothesis must predict new results that can be confirmed by experiments. So once those criteria are met, it is termed a theory. An example of a theory that's currently widely accepted in the science field is the Big Bang Theory. So currently all of the evidence that we have about how the universe started scientifically supports the Big Bang Theory. Until there is scientific data that contradicts that theory, then that's what's accepted in the science field. There are plenty of other theories as well. And laws are a little bit different. So laws are scientific observations that are always seen to be that way without any exceptions. So an example is the law of gravitational attraction. We've always observed that anything that has mass has some level of gravitational attraction to it. So laws are based on observations. If there were ever an observation that contradicts the law, then the law would not be a law anymore. But that's how we generate laws. Theories are different, where they are generated from a hypothesis that is proven true from experiments. Okay, any questions here? Move through that a little fast, but that's the end of this section before we go to the next one. Okay. So we're switching gears a lot, going to the International System of Units. So chapter 1 is an introduction to a lot of different topics that will help us communicate about science in all of the future chapters. So that's why we're kind of shifting around in a lot of different places. The next few units or the next few sections flow together pretty well though. So I don't know if I mentioned, but I went to and visited a friend in Seattle this summer, and we hiked pretty close to the Canada border. And as we were coming back, so we went to a lake, and then as we were coming back, there was another hiker that was coming through, and he was telling us how he came here 10 years ago, and it was 37 degrees Celsius, and they were able to swim in the glacial lake. My friend looked at me, who doesn't work in science, like, how hot is 37 degrees Celsius? We don't use Celsius normally in the United States. It's almost 100 degrees Celsius, or 100 degrees Fahrenheit, by the way. So the International System of Units is a set of units that are used across countries to communicate science. Make it easier so that we're all talking in the same units, communicating in the same units, so that one country doesn't have to be converting to others. So we'll learn about what those international system of units are for different measurements. And then, so our goal here is to recognize these units and then prefixes to convert measurements between units. You might notice it's called International System of Units, but we abbreviate it as SI units, so we switch the S and the I. I looked that up this morning because I didn't remember why that was the case, but the abbreviation is from the French way to communicate international system. So they switch system and international, so we say SI units. Okay, so our base SI units are on this next slide here. We have a couple tables that we'll go through before we do an example. Nothing for you to write down just yet. So our SI base units for length is the meter. By the way, for whatever reason, the United States wanted to make things complicated. We use miles, we use pounds for mass instead of kilograms. We use Fahrenheit, which is pretty unique from other countries. Anyway, so for length, we use meters. For mass, kilogram or grams. For time, seconds. Temperature is Kelvin, which is very closely related to Celsius. For amount of the substance, we use a mole. Electrical current is ampere, and then luminous intensity is a candela. So these are the standard units for different types of measurements depending on what we're measuring. Then we can use these SI base units to calculate physical measurements that require some combination. So like area is length times width. The SI unit for area is meters squared. Volume, length times width times height. SI unit is meters cubed. Velocity is distance over time, so the SI unit is meters per second. Now, for really large and really small values, on the next slide here, we have prefixes that indicate the power of 10 by which the unit is multiplied. So 1 kilogram, we use kilogram a lot. The kilo indicates that the gram unit is multiplied by 10 to a power of 3. So 1 kilogram is 10 to the third grams, which is equal to 1,000 grams. 1 milliliter, this should be 10 to the negative third, not 10 to the third. 1 milliliter is 10 to the negative third liter, which is 0.001 liter. So generally it increases in powers of 3. So we have kilos 10 to the third, then megas 10 to the 6th, gigas 10 to the 9, teras 10 to the 12th. When we go to less than 1, a decimal, we have decid for 10 to the negative 1, centi for 10 to the negative 2, and then we go negative 3, 6, 9, 12, 15. So on the next slide, we're doing some conversions here. I'll do the first one, and then I'll have you all work on the rest of the table. Before we start, change the V to an A, an ampere. Okay, so if we have a 10 to the negative 12th meter, that's the measurement with base units. The base unit with the appropriate prefix, now I go to the previous table, 10 to the negative 12th is a pico. So 10 to the negative 12 meters is 1 picometer. So take a few minutes to fill out the rest of the table, and then I'll go through it as well. For mass, use grams on this side instead of kilograms. That will be here. And then we have grams down here as well. Okay, let's spend a few minutes there. And then if there are any questions, yeah, go ahead.
So where do we use that list? I'm like, where's our example?
So where do we use that list? The previous slide?
Yes.
So there are some of these, I will know on Wednesday which ones. There are some of these I will expect you all to remember. Things like kilo, milli, those are used very widely in chemistry that it's very useful to memorize those. We don't really see 10 to the negative 18 very often. So I'll let you know exactly which ones, but if you can spend time remembering these, then that's helpful. Okay, feel free to talk to the people around you too. It doesn't have to be an independent activity. don't know, that you're, just say I can't. Well, so that's the difference between in and flow and air we have and we have ocean. Well, this is, there are elements here, but air is the combination. So what sort of combination is Oh, I would have to. Yeah, so you think like they. Oh, fine. Okay, let's go through these. So if we have 1 gigagram, the capital G refers to 10 to the negative or 10 to the positive 9 grams. So here we have 10 to the 9 grams. For 10 to the negative 9 seconds, 10 to the negative 9 is a nano prefix. So this is 1 nanosecond. A kilometer is 10 to the 3 meters. So you want to make sure you want to make sure the base unit is being transferred over. And then in this column, we have a prefix, the milli, micro, nano, giga. In this column, we don't. We just have the base unit. 10 to the 6 amperes is a mega ampere. So 1 mega ampere. 1 microliter is 10 to the negative 6 liters. 10 to the 12 grams is 1 teragram. That's what that is, right? Yes, teragram. And then 1 millimole is 10 to the negative 3rd moles. Okay, any questions on those? Were there any that you all didn't get? Okay. Let's do the next one. Check the following that are true. Do the question on the next slide, and then in like 2 minutes, we'll finish up this section, and then we'll end there for class. So try this one and the question on the next slide. So each column, one of these is gonna be true. No, that's not true. No. Don't forget what I said, that's not true. And then when you're done, go to the next slide as well. Okay, let's go through this. 1 megahertz. Mega is 10 to the 6th. So a megahertz is 10 to the 6 hertz, which is exactly what that first one says, so this one is true. For the second one, we have 10 to the 6 megahertz. So a megahertz is 10 to the 6 hertz. And if we have 10 to the 6 of them, then we have 10, just so many, more than 1 hertz. So this is not true. One megahertz, again, 10 to the 6 hertz, not equal to 10 to the negative 6 hertz. So this one is also not true. One conversion that we could do that's not on here is 10 to the negative 6 megahertz. That would be equal to 1 hertz. 10 to the negative 6 times 10 to the 6th. Those cancel out and we have 1 hertz. Okay, questions about these before we go to the next one? Okay, 1 nanometer, is that equal to 10 to the 9 meters? No, it's not. One way to think about this without even looking at the chart, if you remember that nano is really small, and they're putting 10 to the 9th, with this, which is a really large number, in front of the meter, then those we know are not equal. A nanometer is much smaller than a meter. But if we have 10 to the 9th nanometers, then we have 10 to the 9 times 10 to the negative 9, that's the nanometer. Those end up equaling 1 meter. So this one is true. And then 1 nanometer, 10 to the 9 meter, that's the conversion that's present in the table. That one's true as well. Questions? Yes. The fifth one? Yes. So 10 to the 9 nanometer. A nanometer equals 10 to the negative 9 meter. And then if we have 10 to the 9th of those, like this is saying, we multiply 10 to the 9 times 10 to the negative 9. We add the exponents together. We get 0, 10 to the 0, which is 1. That's 1 meter. What's larger? 1 megameter, 1 millimeter? Mega. Okay, we got 1 minute left. I want to cover temperature in the last minute because it's on your homework. So the SI unit for temperature is Kelvin. It is very easy to convert between Kelvin and Celsius. Kelvin is 273.15 units higher than whatever the Celsius unit is. So the freezing point of water is 0 degrees Celsius. The freezing point of water is 273.15 Kelvin. Converting between Celsius and Fahrenheit is a little bit more involved. There's fractions in addition or subtraction depending on which one you're converting to. I can't remember. You might need these for your homework, but you might not need those. I don't remember. But we use Kelvin in science because the absolute zero, where zero thermal energy is present, which I think is impossible to reach, is 0 Kelvin. That's absolute 0, 0 Kelvin. It's negative 273.15 degrees Celsius. 0 Kelvin, that's useful for science. But the important thing here is that the unit size on Celsius and Kelvin is the same. So 1 temperature increase or 1 degree increase in Celsius is equal to 1 degree increase in Kelvin. That's why they're directly related just by that 273.15 change. So the boiling point of water is 100 degrees Celsius. The freezing point is 0 degrees Celsius. No matter if you're working in Kelvin or Celsius, there's 100 units difference between freezing and melting point for water because each unit is equal. Each unit change is equal in Celsius and Kelvin. All right, thanks everybody. We will start 1.6 on Wednesday. Yes. Yes. Yeah. Yes.
It was for this one.
Yes.
I was a little bit confused because when I looked at the chart, it said giga. So then I thought, I'm like, okay, it's wrong. But how did you get the negative?
For the 9, for that?
Mm-hmm.
Okay. So the negative is the nano. So if we go back here,
Yeah, that's
10 to the negative 9 is nano. And so they said, or this question is 10 to the 9 of 10 to the negative 9 meters. So if we have 10 to the 9th of these, those 10 to the 9 and 10 to the negative 9, that means we end up with 1. Because to simplify this like multiplication here, you would add the exponents together, we get to 0.
Okay. Oh, I get. Okay, so it's 2 separate things.
Yeah.
So we're doing giga, and then you look up nanometers, and you go to that, and then you time. Okay.
Yes. Yeah.
Okay. Thank you.
You're welcome. Yeah.
So I did Achieve before, and now it's not working. So this is like the old course, the do not use course, but then this is the new class code, and then nothing comes up.
Someone else had that issue too. Okay.
Yeah, okay.